Now that we know something about a datum and a datum feature, what we're going to do today is look at combining datums into what we call a datum reference frame. The datum reference frame depends upon the order of the datums in which they appear, and I'll explain that a little bit later. So datum order will be critical. And you should be able, at the end of today, be able to identify the datum reference frames within a design specification. What is a datum reference frame? Well, as we learned last time, what we're trying to do is be specific about a relationship between part features. So when we think about a datum reference frame, we're describing one or more datums that are limiting the degrees of freedom. Again, what we're trying to do is control something about position or orientation. What it helps us to do is create some type of coordinate system to reference the nominal, where the true location should be, and the actual geometries that we have after we manufacture a part. Most commonly, what you're going to see are mutually perpendicular datums. Now, of course, that varies a little bit, and we'll see that later on. And certainly if I'm using a point as a datum, the notion of perpendicularity doesn't make sense. So that's kind of a special case. But in most cases, what you're going to see are a set of datums that are mutually perpendicular. And when we make our parts based on the datum features, we'll estimate the datum based upon surfaces that we see. Of course, this will affect the location and orientation of the datums and therefore the datum reference frame. So here's a very simple example of three planes from three datums that are used together as a coordinate system, and you can see the intersection of those planes represent the axes, and the origin is the corner here where all three planes intersect. So let's think about a datum reference frame on an actual part. The location and orientation of that datum reference frame will depend on the sequence in which we put the datums together. And also note that there will be inherent error in the location and orientation of this reference frame, and that's because the surfaces are not perfect. So each part will have its own unique reference frame because of this inherent error. Now down here I've got the same three planes as we had in the previous slide, and we note the sequence in which these frames are being put together. So in this case, the back plane here, 1, is the first one, and then this plane, 2, is the second one, and 3 is the third one. And all I'm doing over here is changing the sequence. So this bottom plane is the first one, the back plane is the second, and the side plane is the third. Now these are not equal. Why aren't they equal? Well, because what we're going to see is the sequence determines the orientation of the planes. So the first plane in the sequence is unconstrained. And we place that up against the surface, and then we construct plane 2 such that it's perpendicular to plane 1. So plane 1 is a constraint on plane 2, and of course for plane 3 it has to be constructed perpendicular to 1 and 2, so again that is a constraint. If we change that sequence, then the actual planes themselves will be in different orientations and positions, and therefore the origin here in the corner will be in a different location. So it's critical that you understand the sequence in which this datum reference frame is going to be constructed. So here's a prismatic feature, and we're constructing a datum reference frame around it. You can see our three planes. The sequence, as we said, is important. So the order in which we construct this plane, if this is first, then we're going to find that back surface. However, if this side is first, then we're going to construct this plane with respect to this surface and then make the subsequent planes perpendicular to that plane. Once we put all three planes together in the correct sequence, then we have a coordinate system, and then if I have other features on here which I'm not showing, we can reference those with respect to these planes. In other words, we can control position and orientation. Here's an axial example, and it may be a little hard to see, but we're using the top of the cylinder as a datum. So the top of the cylinder is a datum plane. And then we're using the axis, which you can represent as two intersecting planes. Note that the axis is perpendicular to this plane. So we're going to construct a datum reference frame, and now we can talk about, again, the position and orientation of other features with respect to this datum reference frame. So the million-dollar question here is, and I should have asked that previously, maybe let's go back and do that for this example. The question here is, have we constrained all 6 degrees of freedom with this datum reference frame? And if you look at the first plane, whichever one is designated the first one, that removes 3 degrees of freedom. The second plane will remove 2 degrees of freedom, and I'll leave you to confirm that. And then the last plane will remove 1 degree of freedom. So yes, we have constrained all degrees of freedom. Let's go again to our example with the axial. And we have the same question. If I have a plane and an axis, have we constrained all 6 degrees of freedom? And you should be able to identify that no, we have not constrained all 6 degrees of freedom. So there is some ability to deviate, and that has to do with rotation about the axis. So essentially our datum reference frame looks like an axis perpendicular to a plane. Clearly, if I have another part feature that I relate, it can rotate about that axis and still be in the correct location and orientation. Okay. So, how do you know you have a datum reference frame? Well, a datum reference frame will appear in the feature control frame. And that's the only way it will appear. So, look at your feature control frame, and it makes up the last sequence of blocks in that feature control frame. The order is important. So, if you recall, in our feature control frame, this is our symbol. This is the size, or refers to the size of the tolerance zone. And then the last set of specifications correspond to a datum reference frame. Now I've colored these just to indicate that red is the primary. That will have the most impact on your result because you will establish that datum reference frame first, and we'll look at examples of that. Secondary, that will have less of an impact because that has to be arranged with respect to A. And then the tertiary will have the least amount of impact, and that has to be established with respect to A and B. So don't forget, order is important. It goes from left to right. So this is first, second, and third. Okay, so what is this effect that we see in the order? Well, we said before in our two examples that if it's the primary, then it's unconstrained. So I can determine that datum without considering any other datums. But when I do the secondary, now I'm going to be constrained by the primary. So I can't determine the secondary datum independent of the primary. And of course the tertiary is dependent on both of those. Note also the same datum can be different in different frames. Why is that? Because of the order. So in terms of the actual location of the datum and its orientation, it could change depending upon where it appears in the datum reference frame. So how do you know you have a datum reference frame? First of all, find that feature control frame. That's going to tell you the information you need to determine the datum reference frame. And then locate your datums, A, B, and C, determine the theoretical geometry as we did previously, and then combine them in the proper sequence to create your datum reference frame. Again, that sequence is determined by their appearance in the feature control frame. So going back to our example here, we see we've got a feature control frame, and in that feature control frame we have 3 datum references in sequence. Again, order is important. So when we think about building the datum reference frame, we proceed left to right, starting with datum A, which we know to be a plane, followed by datum B, which we know to be a plane, and then finally C. And of course, we have to construct them so they're mutually perpendicular. So you can see A being the bottom of that plate, B the left face, C the back face. And now we've got a coordinate system based on an origin being corresponding to this corner here at the bottom. So once you've identified your datum reference frame, then you can use that to control position and or orientation. In example 2, again, we see that we have two datum references in the feature control frame. So what we'll do is construct A first. A, as we said, is the 2D annulus corresponding to a plane. And then B corresponds to the outside cylinder. Therefore, we're dealing with an axis here. And I've shown that axis as the intersection of two planes perpendicular to A. So we've got a datum reference frame where B is perpendicular to A. Again, order is important. If we do that in reverse order, it's a completely different datum reference frame. In example 3, again, this is the simplest case where we only have one datum reference. And so we can construct that obviously independent of any other feature. We're looking at that feature and therefore the axis. Oh, wait a minute. Yep. We've got datum A here. Can't see that, but that is datum A. And so we're dealing with that axis, which I show here as two perpendicular planes corresponding to A, which is an axis. Finally, in example 4 here, we have three datum references, and A corresponds to A corresponds to the bottom of the plate, B corresponds to the outside cylinder, and then finally C corresponds to this slot feature here. Well, how do we construct that? Again, we're going to start left to right with A being the primary, and we have a plane corresponding to A. The next one is B. B we see is that outside cylinder, and therefore we're dealing with an axis that's perpendicular to A. And then finally C. C again is that nuance case in which we're attached to the dimension line, as you can see here. Now that would be very different than if we attach C to the extension line. So if we had something like this, then the datum is completely different, right? Then we would be talking about this surface. But as we can see, it's attached to the dimension line, and therefore it corresponds to the slot feature as described by these two surfaces, and therefore it is the midplane of those surfaces. Now note, in this case, C, based on the geometry here, is going to be perpendicular to A. But clearly, C is not perpendicular to B, but parallel to B. Now the million-dollar question here, must B be contained in C? The answer is no. There's no constraint on that. So C is just created parallel to B, and in fact, when we actually make a part, it will not contain B because all the parts are imperfect. And then C, of course, is perpendicular to A. So at this point, you should be able to construct a datum reference frame from a set of datums and understand that datum order is important. And why is it important? Because it changes the position and orientation of the datum reference frame. Primary datum, that's the first, secondary, tertiary. Primary has the most impact on the position and orientation of the datum reference frame. Secondary, less. Tertiary, even less. And we'll see that in examples. In summary, datum reference frame can have one or more datums. Simplest would just be one, such as an axis in the example we've already seen. The datum reference frame is defined in the feature control frame, and the order of datums will affect the location and orientation of the datum reference frame. This principle is very important because that will determine whether or not your part is within specification if you're using the correct order. If you're using an incorrect order, you can get yourself into trouble. Okay, so given that we can construct the theoretical datum reference frame, how would we actually create it on a part that we've just manufactured? So let's think about that. The first thing we need to understand is this concept of a mating envelope. And that's going to be important not just in the context of a datum reference frame, but we'll use that in other contexts as well. And then we'll look at a material condition envelope, again based on MMC or LMC, and also the material condition effect on the envelope. So if I deviate from material condition, how does that affect the resulting envelope? So when we actually create a datum reference frame on a part that we've just manufactured, we should think about our datums in the prescribed order. And so we'll try to establish them. By establish, we mean locate and orient our part with respect to that. And if it's a planar feature, then you can think back to IE 248, which you used a surface plate for flat surfaces. And a surface plate is, of course, a precision ground surface that approximates a plane. Of course, it's imperfect itself, but it is a close approximation of a plane and helps us identify where that plane is for the surface. A feature of size is different. We introduce that concept of a mating envelope here. And here we'll use the complement of a datum feature. And by the way, this mating envelope is a theoretical geometry. In other words, it's a perfect geometry, which means it doesn't exist. But if you think about the feature itself, you take the complement in terms of a solid feature. We're going to find the minimum enclosing envelope. So think of it as being shrink wrapped around that solid feature, a protrusion of some kind. And we're going to shrink a perfect geometry around that, and hence we call it the mating envelope. For an internal feature, an empty feature, we'll take the largest theoretical geometry and expand it. Also note, while we're doing this, the datum that we're establishing must be oriented perpendicular to the previous datums in the datum reference frame. So let's look at our example. We can use a surface plate here to establish B, or establish A first, and that's indicated by this plate here. And then B, we bring in a surface plate perpendicular to A. And then C, we're going to bring in another surface plate, and that's going to be perpendicular to both of those. And you can see here our part that we've created is now established within that datum reference frame. Note, and let's just enlarge it, when we bring that surface plate for B in contact with B, so if we kind of expand this and look at the actual surface, and I'll exaggerate this, let's say that B, due to our manufacturing process, is actually at an angle to A that we've already established. Note what happens here is we bring in the surface plate. As soon as we make contact, which would be at this point, that determines where B is. And that's why order is so important. We've already established A, so we've got this little space in here that I've exaggerated that shows you that the position of that side is again affected by our order. If we were to establish B first, then we would have the plate come in contact in this way, and you can see the difference in terms of the orientation of the datum reference frame. In example 2, again, A corresponds to a 2D annulus and therefore plane. So what we'll do is create a surface plate here that establishes that 2D annulus, and then we'll bring in this mating envelope, which would be the smallest cylinder that fits around B. All right, so we're kind of shrink wrapping a perfect cylinder around B while maintaining its perpendicularity to this surface plate representing A. And therefore we establish an axis for B perpendicular to A. Example 3 obviously is a lot simpler. Here again we see datum A corresponding to the large half cylindrical slot, and in this case all we have to do, because it's an internal feature here, is find the largest cylinder that will fit, perfect cylinder again, that will fit inside. So you can see here I've created the largest diameter cylinder that will fit in that half cylindrical slot, and now I can orient something with respect to that because I know where the axis is of that feature. In example 4, we have our 3 datum references. Again, A is going to be a surface plate that we bring in contact with the surface here, and now that establishes A. B is next. Now we take the minimum cylinder perpendicular to A that determines the axis for B, the mating envelope, and then finally for C, the mating envelope would be the largest box, essentially 2 parallel planes, that we can fit in the actual slot, right? And that box is going to be oriented with respect to A, and of course parallel to B. So once we place that box in there, then essentially we've established the location of this midplane. Now what happens when material condition comes into play? And how do we know it's part of the equation here? Well, what you're going to see in your datum references, if you have a feature of size that has a material condition, as in this case B, then similar to what we saw for the feature in this tolerance zone size box here, was that additional tolerance is allowed as the feature deviates from material condition. Well, the same will apply for datum references. In other words, we'll allow the position, in this case, to vary even more if the feature of size itself is varying. So when we think of a datum feature of size, we might think of a cylindrical type of feature or a slot kind of feature, as we've seen before. If it's regardless of feature size, then of course the mating envelope is used to establish the datum. The datum is always constrained by any previous datums if we're secondary or tertiary. If we're at MMC, then we're going to use the MMC condition envelope and not the mating envelope. And then of course if we're at LMC, we'll use the LMC condition envelope and not the mating envelope. Of course the orientation location, we still have that constraint. Well, let's take a look at this material condition. As you can see on the left, if I'm using that feature as a secondary or tertiary datum, and I've exaggerated the deviation of that feature, you can see the axis will be determined by our constraint that it be perpendicular to this other datum. So this could be serving as a datum, or this surface could be serving as a datum, and now we've oriented. Note the mating envelope. The mating envelope is a perfect geometry, and we're trying to enclose this feature and establish it. And the width of that mating envelope is W1. Now what happens when the feature is independent? In other words, it could be the primary datum reference. Then we see a different orientation of our mating envelope. Again, the smallest cylinder that fits around that. Clearly, W2 will be strictly less than W1. So we can see that we have this effect on the material condition depending upon where we are in that order. So our envelope will affect the material condition based upon the size. So W1, again, greater than W2. And we'll see other examples of that as we go along. So what happens when we deviate from material condition? Well, think of it this way. In this context, we have a mating envelope, and let's say we were to use this red zone here as a way of establishing the datum. And in this case, it has a much greater width than if we take the material condition envelope. Let's say it's MMC. So MMC in this case is smaller. So we can think of this as being, let's say, a hole feature. It would be the smallest hole diameter, and therefore the MMC envelope for this datum would be the smallest dimension possible, again oriented with respect to other datums if necessary. However, if we were to use a mating envelope, it might actually be larger because the actual hole deviates from material condition. So when you're establishing a datum that has a material condition, you're going to use the material condition envelope, not the mating envelope. Now, what is the net impact of that? Well, you can see the difference between the two. What that is saying is you're going to allow, because it's smaller, greater variation in position and or orientation, because again, we're not contacting the surface with the material condition envelope. The mating envelope comes in contact with the surface of the hole. And so there's kind of this wiggle room as indicated by this excess on the left and on the right. And we'll see that in other examples as well. So the key concepts here, again, when do you use the mating envelope? When you have a feature of size and there is no material condition on that datum. And then we saw a material condition envelope that is fixed at either MMC or LMC. And of course, datum order has an effect on the envelope, as we saw, because if we orient the mating envelope with respect to a datum reference, we're going to get a different width than if we do that at the original or primary datum surface. So the mating envelope is always based on the nominal geometry. It's a perfect geometry. If we're using the material condition, the orientation and location of the datum can be affected. And the deviation from material condition is based on differences in the envelope sizes, again, between that mating envelope and the material condition envelope.